Hello and welcome to this new lecture of artificial and robotic vision systems. Today I will express you some of my thoughts and tips regarding deep learning and in particular on deep networks. So deep networks and deep learning are one of the top models now to model synthetic vision system, in particularly human visual system. I will talk about experiments that I conducted and my thought on the field as it stands off right now, and ideas to what should be done and how it should be done. Also, I will go into a little bit more details about some subtle issues about deep learning that we didn't cover in the previous lectures. So as we saw previously, deep networks are basically composed of a variety of layers. There's an input image or an input data. There's multiple layers, so these layers are usually maintain a map that is retinotopic, meaning they maintain the spatial coherency of objects that are the same as the input image. And there are multiple layers that squeeze the information until information is reduced substantially, and it can go into an output classifier that then can classify and give you the results you want. This is the standard architecture that we've been looking at. Looking back at one layer, we saw that each layer receives n inputs. It does some convolution correlation with some filters, which does a combination of these input and inputs, combines them into another set of outputs or maps. These are kind of like the output of the neuron output maps. Then they could be followed by subsampling, and definitely have to go into some linear modules so that you don't combination of multiple modules doesn't collapse to a single linear module, and that's what you want to create more invariance and separation between layers. So usually on a deep network like the one we've seen in the last few lectures, what happens is you have to repeat a sequence of actions, of things to do to train this network. So what you usually do is you sample the output of a network of the previous layer. So you cluster this input and you create some filters. You either cluster or do some other learning technique. And then you use this filter to generate these output maps. Then you can do subsequent pooling, normalization, and so forth. So deep networks are defined. If you look at the entire network, they're defined by a set of parameters. This set of parameters are the size of inputs and the number of layers. So how big are these layers maps and how many neurons do they have? It really all depends on a combination of parameters. You want to know how big is your input, because the bigger the input, the more operation you're going to have to do. Since if we're talking about images, the larger the input, then you're going to have a quadratic increase in computation due to the more size. You also want to figure out the number of filters, number of layers, and also the connection between layers. So you want to figure out how many layers am I going to have. It depends usually on the invariance that you can get from one layer, and if that's enough for your task. How many filters on each layer is important, because you want to be able to extract all the information at each layer as effectively as possible, and usually having fewer filters or kernels in the first layer speeds things up, because That's where you have the most computation to do. So the more filters there are on the first layer, the more computation there will be to do. So in fact, the deep network, usually the total number of computation can be approximate by, usually, 1.5% of, or usually the number of operation that you do on the first layer, really. You also want to specify the connection between these layers, so how are these things connected? And you also want to specify the pooling layers. And what kind of filters or learning techniques that you want to use, which we talked about a little bit in the previous lectures. So deep networks, if you think about it, they are basically defined by some kind of an architecture. So going back to the slides, this is the architecture. Graphical representation of the architecture is, how many filters do I use, how many layers do I use. Once I decide all of this, then you usually go into what nowadays is basically learning and training. So you train kernels and filters at each layer. You also train the connection between the layers. But really, architecture should be a parameter that should be learned. There has to be a little bit more work here that it's more difficult to do, but it's quite more important, as we see that some of these networks, for example, perform quite well even with random parameters. It means that sometimes it might not be the actual filter that makes the difference, but it might be the architecture. I haven't seen a lot of work in this area, at least with results that, large-scale results, basically. That's probably one of the most important areas to work on in the future. Because really, like we learn filters and connection, all the networks should be learned together from data, as much as possible, at least, because the data has to tell you what kind of organization in the network it needs, so that you can extract the information that you are after. So I will, in the next few slides, I will report some of findings of experiments that I ran on a supervised deep network, and also partly supervised. For more details about what I'm going to say and things that might not be clear in this lecture, I really recommend you to read the references that are at the end of this lecture. So there's a nice list of groups. The more paper you will read from these groups, especially the key ones or the most recent ones also, the more you will be able to understand about deep networks. And really the only other way to learn deeply about this field is to do some work yourself.